Hi guys, I'm back, and this time we're going to talk about water. So in our textbook, that is chapter 11, and we're going to break this up over 2 weeks since it's such a big topic. This week we're going to talk about water resources, so kind of like water quantity, how much water there is, and where it is. And then next week we're going to talk about water pollution, water quality issues. So I'm going to share my screen here. There, and then I'm actually not on the first slide. Slideshow in the beginning. Okay, so the water resources is the first half of chapter 11, chapters or sections 11.1 through 11.4. Okay, so first of all, there's a lot of water on our planet. However, most of it's in the ocean. About 97% of all the water on the ocean, or all the water on the planet, is salt water. So that's not really accessible for organisms in terrestrial ecosystems. So the fresh water, what's going on with the fresh water, is in many ways more interesting to us. And of that water, it is in different what we call reservoirs, which doesn't necessarily mean man-made lakes to store water, but means a kind of location on the earth or in the environment where water can be stored or exist for a period of time. And by far and away, the biggest reservoir for fresh water are ice caps and glaciers. So these are getting smaller over the last 100+ years, but they're still massive compared to other freshwater reservoirs. About 77% of the fresh water is stored in these locations. And while some ice can only exist for a short amount of time, right, a snowflake might fall and then melt out later that afternoon, sometimes water in these reservoirs is stuck for hundreds of thousands of years. So we have water that has been in glaciers, in Antarctica, in Greenland for close to 1 million years. And so it's not really circulating in the environment as readily as other sources of water. The second biggest source of water is called groundwater. And groundwater we'll talk more about later, but this is not necessarily the water that's bonded to like the very surface soil particles in the ground, but it's the water that's kind of deeper down in a saturated zone. And this is a big source of water on the planet as well. About 22% of the fresh water is in groundwater, and these the water that gets down into the groundwater also has a longer what we call residence time, meaning once it gets into this reservoir, it is much more likely to stay there for a long time, like thousands of years. Okay, then all the other sources of water or locations where water might be stored, lakes, soil, the atmosphere, rivers, living organisms, are all, you can see, orders of magnitude smaller in terms of the reservoir size, so like less than 1%, or in many cases less than 0.1 or even 0.3% of the water is existing in these sources. They tend to have much shorter residence times though, so the water is cycling in and out of these systems, it's moving around in the environment. And then of course these are just the kinds of sources that are much more readily accessible to many terrestrial organisms. So we have a lot more kind of connection with these sources, and they're very important to us in terms of our water resource and accessibility. Okay, so however, let's acknowledge the first two components, the ice and the snow and the groundwater first, before we get into some of the surface water issues. And ice and snow is an enormously important sort of water storage device. As we already said, sometimes we might have ice and snow that lasts for a small amount of time, but sometimes we have ice and snow in glaciers that has been there for hundreds of thousands, close to millions of years. And we know that as the glaciers are melting, this transfer of water from these terrestrial freshwater systems into the ocean system is causing significant sea level rise. And we've already talked about that, so we're not going to talk about it again, but that's certainly a water kind of resource issue. But another way that snow and ice is very important is that water in its frozen form, in a snow form, provides an important water storage reservoir on the landscape. So if we have rain that falls on the ground, that rain quickly runs off, ends up in rivers, and then maybe quickly in a matter of days or weeks washed back out into the ocean. And so we don't have it for future use on the landscape. Whereas if water falls as snow and then stays frozen as snow for months, then it may melt more slowly. Be more likely to, as it melts, kind of infiltrate and be stored in the soil. And it may be just kind of released to the environment as it melts many months after that precipitation event has occurred, and be available for both environmental use for different kinds of organisms and of course for human use at a much later time in the year when we might not have as much new precipitation falling. So especially in places like California and in other parts of the West where we have high mountains and then dry summers, we have historically been very, very dependent on our snowpack as to provide an important reservoir, right? We don't have reservoirs, like meaning man-made lakes like Oroville Dam and stuff, that allow us to hold nearly the amount of water that we depend on and expect to be able to use in the summer and fall. And instead, we have depended on the snowpack to provide this natural reservoir to us. And unfortunately, as the earth is getting warmer and our winter temperatures are warmer, we're having much more of our precipitation fall as rain, not as snow. And this is really disrupting our ability to access this fresh water later on in the year. So we do a lot of research trying to understand about where the snowpack is, because we know it's so important to our water resources and water access. And when we have drought years like we did in 2013, 2014, 2015, we have very, very limited snowpack. So you can see this picture in the left showing how limited snowpack there was in the Sierra Nevada. So you can see this is like the boundary between California and Nevada. There's Lake Tahoe right in the middle. And then you can see in 2017, which was above average year, what it looks like when there's a lot more snow. And so that you can imagine this is snow that we will have access to use many months from the time that it falls from the sky. So again, there's a lot of concern that already we're seeing a smaller snowpack, and in the future, as we have every expectation that the world will continue to have average warmer temperatures, we'll continue to have smaller and smaller snowpacks, even if we have the exact same amount of total precipitation, which we also think is probably not true. But even if that was the case, our snowpack would be getting smaller. And so this is a particular research project that was done, published by the Climate Change Center of California Energy Commission. And so it's showing by mid-century that the Sierra snowpack will be down 20 to 40%. And then by 2021, the snowpack could be down by 90%. So this is kind of a scary prospect. And like all these things, what's really kind of an important takeaway is, one, we should focus on trying to minimize warming as much as possible, but also we need to be prepared for some inevitable changes which are certainly coming our way, and we need to think about how we're going to distribute water, use water, regulate water, have proper infrastructure to deal with water in a world that's going to look different than the world that we've been used to in the past. Okay, so this is particularly important in parts of the West, as we've already said, that have like high enough mountains to have decent snow fall in the wintertime, and then dry summer season. So we experience what's called a Mediterranean climate, meaning that we get our precipitation in the winter, and then we have the growing season, the summer, the warm period with very little precipitation. That might seem very normal to you. It seems very normal to me, but that's actually a sort of atypical climate pattern worldwide. And so, again, because of this, when it's cold, we're getting our rain or snow. The snowpack is able to act as a natural reservoir. And in California and other parts of the West, 75% of our fresh water that we use in the state comes through the snowpack. So this is showing kind of these wet winters and then dry summers, wet winters, dry summers, the seasonality of our precipitation. and a real need to have some water stored on the landscape to provide us water in the summer and fall. Okay, so the other issue is when we don't have snowpack, then we have all this precipitation falling in the mountains and rushing down through the rivers and meeting our kind of man-made reservoir systems all at once. And the reservoir systems that we have and the communities that we've built along the edges of rivers were not having the expectation that they would be receiving so much precipitation all at once, because at the time that these projects were designed and built, a lot of the precipitation that fell in the winter was falling as snow and was sticking around on the landscape, again, for months before it was melting and flowing downstream. So in these warmer winter storms, we're increasingly having major flood problems, and we're having some kind of dam management problems. You probably remember a few years ago, there was this major scare where the Oroville Dam was overflowing, and then it was not quite clear if the dam and the overflow system on the dam had proper strength to hold up the water that was behind it, and they had to do this major evacuation of people below the dam. Luckily, the dam held, but this is, again, kind of an illustration that our current infrastructure is not built to deal with the current water situation that we have in this new and warmer climate. Okay, so another thing that's kind of important to keep in mind is that the water amount that comes into California is always uncertain. We don't have really a consistent amount of water, so we can come up with averages, how much water we get on average. But what we just do know is that it changes a lot from year to year, and it always has. And we have always had wet years, and we've always had dry years, and we've always had drought periods, so many dry years in a row, and then wetter periods, many wet years in a row. And when we look back through the record by looking at things like tree ring data and just other kind of historic measurements, what we can see is that while droughts have certainly occurred throughout our kind of more history with a lot of written records in the past several hundred years, that we've had droughts that have existed in the past, and then we've had some really major mega droughts in the past that have lasted for much longer periods of time than what we have considered to be severe droughts in the last 100 or 200 years. So this particular graph shows things like the drought in the 1930s, the Dust Bowl, the drought in the kind of like 20 and the 2000s, a couple drought periods we've had, and we can see that they have dry years that are much less dry and dry year periods that last for a much shorter time than some of these mega droughts that we had when we go back into like 1200 common era time and 800 to 1000 common era time. And so this is also kind of a really important warning for us to understand that if we are thinking about what kind of needs we might have in the future and what conditions we might be facing in the future, one, we know the world is getting warmer, so we're changing our environment a little bit. But even before the world was warmer, we certainly were faced with, or our environment and the different communities of people that lived here before were faced with experiencing droughts that lasted like decades to nearly centuries. And so the kind of drought that we have experienced so far is nothing compared to that. And we should consider what we would do and how we might get ready to be able to kind of have an economy, have industry, and have kind of basic needs met in a much, much drier condition, which we might find ourselves in by the end of the century. So there was, in particular, a big research paper that came out a few years ago that kind of got a lot of people interested in thinking about, you know, how would we be prepared and what could we do? And this particular research paper that looked at like climate proxy data through tree rings and whatnot, going back through time and learning about when it's dry and tree rings are close together, and when it's wet and tree rings are farther apart because of greater growth when more water is available. They're able to look back through this kind of data and then make an estimate that we have an 85% chance of experiencing a 35+ year drought in the Central Plains and Southwest area of our country in the second half of this century. So if we have been extremely disrupted by 3 or 5 or 7-year droughts in the past, a 35-year drought is going to be much more serious than that. It would be much more severe than the kind of drought that led to the Dust Bowl in the 1930s, or that led to the end of the Pueblo Society, going back, many, many hundreds of years. And so again, are we thinking as a society and as a government about what we would do in this kind of situation? Okay, so one of the things that we do in a situation where we find ourselves without the amount of water on the surface that we would hope for is that we turn to the water that's under the ground. So we said groundwater is about 22% of the surface water that's or about 22% of all the fresh water that's available. So if we live in a dry area where there's not as much surface water as we might want, falling from the sky as precipitation during many dry months of the year, or flowing towards us through streams, then we can go underground and we can pump water that has kind of infiltrated down and been stored under the ground for long periods of time. And we call this water groundwater. So groundwater is not all water that's underground. Some water below the ground is called soil moisture. And this is kind of the water that's in the surface environment that's bonded onto soil water or soil particles. And then if you go down in the soil, at some point, you'll hit what's called the water table. And the water table is the boundary between the unsaturated soil on top and the saturated soil below. So saturated means all the space in between the soil particles is completely filled up with water. That's a saturated zone. And that's a zone that we refer to as the groundwater. And when we have large amounts of groundwater in an area because of soil texture or landscape shape, or because there's a lot of fractured rock and gravel with a lot of good pore spaces to hold water, we might have what we call an aquifer, which is basically just a large underground area where a lot of water is stored. And I think a lot of people, when they imagine an aquifer, they think of a big underground pool or cave that's filled with water. And that sometimes can happen, especially in certain geologic types like limestone. But for the most part, water in aquifers and groundwater is just little tiny amounts of water that are stored in between the soil particles. So you can see the picture on the left kind of illustrating what this would look like. And so water builds up in these underground aquifers over long periods of time, kind of depending on how long the landscape has been fairly undisturbed, maybe millions of years or thousands of years. And if we go in and pump water out of the ground using things like wells, then we want to make sure that we're recharging, that we're adding water back down to the aquifer so that it's there for us in the future as well as just today. And we call that process recharging an aquifer. However, recharging an aquifer is not a quick process. We can't have 1 year of rain in the winter and expect that lots of pumping over long periods of time will be kind of washed away by this recharge. But instead, this is something that is kind of a long-term process, and it needs to be consistently done. And if we want to focus water getting down into the ground, we can kind of try to pool or pond water up on the surface above known aquifers and let it sit there for a period of time and hope that that will allow for proper infiltration down to recharge aquifers. So sometimes this is done with reclaimed water. So after water goes to a sewage treatment plant, we might spread it out in the landscape and hope that it has the opportunity to infiltrate down into the water or into the ground, which should also be a purification process. Or we might have certain agricultural systems like rice fields in the Central Valley in California that use flood irrigation. So a lot of water goes out to water the rice, which isn't necessarily great from a water use perspective, but it does allow for an opportunity for infiltration and aquifer recharge. Okay, so we are experiencing a lot of groundwater depletion, or what's sometimes called overdraft, where we're pumping water out from the ground at a much faster rate than we're recharging those aquifers. And this is a problem because lots of people depend on groundwater as their source of water. About 50% of Americans depend on it, and rural Americans are much more dependent. So about 95% of rural Americans are dependent on groundwater, and pretty much anyone in Plumas County is dependent on groundwater. So many of you may be on a personal well, on a more rural property, but even if you're in town, in a place like Quincy, you're actually getting water from a well that then they're dispersing to your home. So unfortunately, when lots of people are pumping water at the same time from the same kind of underground reservoir or aquifer, this usually is unfortunately happening at a non-renewable rate where we're overdrafting these reservoirs. And in some cases, this has become quite serious. So this is an image showing the Ogallala Aquifer, or sometimes called the High Plains Aquifer, which is in the kind of Dust Bowl historic area of our country, the kind of Southern Plains area. And what this is showing is different colors represent the feet of drawdown of water from aquifers that happened between 1980 and 1995. So a little bit out of date, but illustrates these trends. And the areas in red have had more than 50 feet of water removed from the ground. So that is a lot of water. And this particular diagram doesn't necessarily show how much water is left, which is, of course, an interesting thing for us to know. But it certainly does illustrate that this has been a big drawdown and certainly provides opportunity for us to consider and start to be concerned about at what point are we going to run out of this water, and have we built infrastructures and economies dependent on this water that may not be here in the future. And we certainly have these kinds of issues in California as well. So this is a particular research project that's been done trying to understand California groundwater storage and California groundwater overdraft. And in this case, this is done through satellite, through remote sensing, and then it's done with gravity. So gravity is a force that causes things with mass to be pulled towards one another. And the ground that's saturated with water has more mass. It's denser than dry ground that has air in between soil particles. And so we can actually kind of measure the gravitational pull of the land. And when the land is wet, has more water stored in it, it's going to have slightly a greater pull. And so there's a particular program and satellite that's called the NASA GRACE satellite that's been flying around trying to measure groundwater. And what we can see is that we have been losing a lot of water from inside California. So starting in about 2011, through the first half of the last decade, we are losing 12 million acre feet per year from the Sacramento and San Joaquin River Basin area. So an acre foot is an area that's an acre, about the size of a football field, filled up 1 foot depth. So 12 million of those per year are being pulled out of the ground, and that is much in excess of the amount of water that is being recharged. So one of the things that we're seeing is that this water is being drawn down. It may not be available to us in the future. Many people have experienced wells running dry, et cetera, et cetera. But another interesting kind of side impact of this is what's called subsidence. So subsidence is when the surface of the ground actually subsides or is lowered because of what's going on under the ground. So this on the right is this famous photograph that shows the surface of the San Joaquin Valley, so kind of the southern central valley in 1925, where it used to exist, where it existed in 1955, where it existed in 1977, and now it's, of course, even lower as we've continued to have more drawdown from our aquifers. So we can see that the ground is literally collapsing in on itself as we're pulling water out of the ground. And, you know, the particular ground level may not be of great importance to you if you live somewhere like Bakersfield, but it might be of much higher importance to you if you live somewhere like in the Delta area, San Francisco Bay Delta area, where subsidence might mean that you're moving below sea level and starting to experience saltwater intrusion into your water systems or into your property. So we can also have, in extreme examples, what are called sinkholes, when water is pumped out of the ground and the removal of the water kind of reduces the strength of the ground enough. And especially if we have usually like a limestone geology and we've had groundwater kind of carve out these actual underground caverns or caves. And at some point they were filled up with water, and then the movement of the groundwater out of the cave causes the cave to not be kind of buoyantly held up as it was before. And then the ground can all of a sudden, in a very spectacular and horrifying manner, collapse down in to that area where the water is no longer existing. So anyway, the picture on the left is a picture of a sinkhole. But all in all, we've just had much, much less regulation and management of our groundwater historically compared to surface water. So it's been a bit of a free-for-all where everybody is drilling wells on their own and trying to get as much water as they can without a lot of concern about how that might be affecting their neighbors or their future selves. So recently there has been a new law in California that's called the Groundwater Sustainable Use Act or something like that. And it's asked people in these different groundwater basins to work together to come up with their own sustainable groundwater use plan. So it's a very kind of like locally controlled thing, but the idea is they're asking everyone to at least consider who is using water, how much water is being used, and how is that going to be able to affect future use by people in the same community in the same groundwater basin. So it's kind of a step in the right direction as far as groundwater sustainable use. Okay, I'm going to stop there, and then I'll record a second video about some more water resources in a moment.